You know when you hear about like matter and antimatter, right? It's like these opposing forces in the universe.
Yeah.
But like, have you ever like stopped to think if there could be some kind of particle that like doesn't even need an opposite?
Right.
Like a particle that is just in itself its own antiparticle.
Whoa.
It's like something out of science fiction, right?
It does sound like it.
Yeah.
It really does, but as we'll see today, this is like a very real concept. And incredibly intriguing one too in modern physics.
Okay.
And for this like mind-bending journey, we're going to be looking at this essay. It's called Majorana Fermionen, Rätselhafte Teilchen der Quantentechnologie.
Wow, that's a mouthful.
Yeah, it is a bit, isn't it?
Yeah.
And it's written by Jurgo Schneppat.
Okay.
And it's a fantastic resource that really dives deep into these enigmatic particles.
Yeah, absolutely. And that's exactly what we're doing in this deep dive, isn't it? We're going to like unpack this strange but potentially revolutionary world of Majorana Fermions.
Right.
These particles that like blur the lines between matter and antimatter.
Yeah.
And perhaps even more excitingly, we're going to look at why they're causing such a stir in this cutting-edge field of quantum technology.
That's right.
Yeah.
Schneppat's essay, along with kind of like the foundational physics behind it, it really takes us from like the very beginning, like the initial groundbreaking idea, the fundamental principles that are at play. Then it goes through their connection to the world of superconductors, the experimental efforts to actually find them, and finally the truly transformative implications they hold for the future of quantum computing.
Right. Okay, so let's start right at the beginning.
Okay.
Where did this wild idea of a particle being its own antiparticle even come from?
Well, the seed for this idea was planted way back in 1937 by a brilliant Italian physicist named Ettore Majorana. And he was really struggling with Paul Dirac's famous equation. The one that describes the behavior of relativistic fermions, which are like fundamental particles, like electrons, things like that.
Okay, the Dirac equation, the one that's like, looks like a cryptic code.
It does, doesn't it?
Like, I gamma mu, partial mu, 0, 0.
That's the one.
Yeah.
Now, Majorana had this really profound insight. He wondered if there was a way to modify this equation to describe particles that didn't actually need a separate antiparticle. And remarkably, he found a way to do this. And this resulted in what we now call the Majorana equation, which is I gamma mu partial mu on 0. So very similar. But the crucial difference here is this condition. Since Simocock, think of it like this. Imagine a particle where flipping its charge doesn't create a brand new opposite particle. It just brings you right back to the original one.
Oh, wow.
That's the essence of this condition.
Okay, so that's already like mind-blowing right there.
It is, yeah.
And then to add to the mystery, isn't there like this whole story about Majorana's sudden disappearance in 1938?
Yeah, there is.
It's almost like his incredible idea is shadowed by his own enigmatic vanishing act.
It is. It truly is one of the most enduring mysteries in physics. And what's so interesting is that for a long time, his theory kind of flew under the radar. It wasn't really until much later that his ideas resurfaced and started to gain some serious traction in two seemingly unrelated areas. The study of neutrinos. And as we'll dive into the physics of materials, specifically solid-state physics.
So before we like go any further, let's just nail down some of the basics. What exactly are fermions? And why is this whole being your own antiparticle thing so unexpected?
So in the world of fundamental particles, we've got two main categories. Fermions and bosons. And fermions are like the building blocks of matter, like electrons, quarks, and neutrinos. And they have this property called half-integer spin. You can kind of think of it as like a tiny intrinsic angular momentum that comes in multiples of like half a fundamental unit. And a really key rule that they follow is the Pauli exclusion principle. Which in simple terms means that No two identical fermions can be in the exact same quantum state at the same time.
Okay.
And this principle is super crucial for how atoms are actually structured.
That's what, dictates how electrons arrange themselves around an atom.
Precisely.
Yeah.
It governs those configurations in atoms, which dictates how atoms bond together and, the fundamental properties of all materials around us.
Okay.
And this principle is mathematically captured by the fact that if you swap two identical fermions, the mathematical description of their state, called the wave function, it flips its sign, psi by 1 by 2 by psi by 2 by 1.
Yeah.
It's like swapping those identical twins fundamentally changes the identity of the room's quantum state.
Okay, I think I'm following so far.
All right, good.
So now, how did Dirac's work change our understanding of these fermions?
Well, the Dirac equation was a monumental achievement.
Okay.
It was the first equation that successfully combined the principles of quantum mechanics with Einstein's theory of special relativity to describe fermions.
Okay.
And one of its most profound and surprising predictions was the existence of antiparticles.
Okay.
So for every fermion, the equation predicted this kind of mirror particle with the same mass, but the opposite electric charge.
Like the electron and its opposite, the positron.
Exactly. The positron, the antimatter counterpart of the electron.
Right.
It was experimentally discovered by Carl Anderson in 1932.
Wow.
And that was a really stunning confirmation of Dirac's prediction.
Oh.
Now, the crucial difference here, the heart of Majorana's insight lies in this distinction.
Okay.
Dirac fermions, like the electron.
Right.
They always have a distinct antiparticle.
Okay.
But Majorana fermions, by their very definition, are their own antiparticles.
Right.
They satisfy that condition Pezifrsic.
So no need for an anti-Majorana fermion.
That's right. Well, mathematically, the self-identity is captured by the Majorana equation, the self-conjugation condition. C bar pi MRT, where C is this mathematical operator called the charge conjugation matrix.
Okay.
And this seemingly small tweak actually has some really profound consequences.
Okay.
Majorana fermions must be electrically neutral.
Right.
Because if they had a charge, their antiparticle would have the opposite charge.
Okay.
And that would obviously violate the condition of being their own antiparticle.
Right, yeah.
And perhaps even more interestingly, they have the potential to exhibit a special kind of stability linked to the topology of the material.
Okay. Topological stability.
Yeah.
That sounds important.
It is.
And a bit mysterious.
It is a bit, yeah.
Yeah. How do these Majorana fermions show up in the world of materials in solid-state physics?
Yeah, so this is where the story takes a really fascinating turn.
Okay.
So while Majorana's initial idea was rooted in the realm of high-energy particle physics, these particles can also emerge as what we call quasi-particles within specific types of materials, particularly topological superconductors.
So quasi-particles.
Yeah.
So not like fundamental particles themselves, but more like collective behaviors that act like particles.
Yeah, you can think of it as like a kind of ripple or excitation within the material that behaves like a particle.
Gotcha.
Now, to understand how this happens in superconductors, we have to quickly recap conventional superconductivity.
Okay.
So in typical superconducting materials, below a certain critical temperature, electrons team up in pairs with opposite spin and momentum, forming what are known as Cooper pairs.
Right.
And this pairing is what leads to that amazing property of zero electrical resistance.
Right. These are like the materials used in incredibly strong magnets, like in MRI machines.
Yeah, exactly.
Yeah.
Now, the behavior of these superconducting materials and the quasi-particle excitations within them can be described by a more complex equation called the Bogoliubov-Dijen equation, often shortened to the BDG equation.
Right.
H text BDG E psi.
Right.
This equation essentially takes into account both how electrons normally behave in the material, like H0, and the effect of the superconducting pairing, which is delta.
Okay, so how does this special equation in special materials lead to Majorana fermions?
Well, certain exotic types of superconductors, known as topological superconductors, they have a very unusual electronic structure. It's called a non-trivial band structure. Right.
as physicists like to call it.
Okay.
And this can lead to the emergence of Majorana states.
Okay.
Defects within the material.
Right.
Like tiny whirlpools of magnetic fields called vortices.
Okay.
Or even at the very edges of the superconductor.
Right.
And these localized Majorana states are often referred to as Majorana zero modes.
Okay, zero modes.
Yeah.
What's so special about those?
Well, Majorana zero modes are quasi-particles that are trapped at these topological defects.
Okay.
And they have this remarkable property of being their own antiparticles.
Right.
Just like the original Majorana Fermions we saw in high-energy physics.
Yeah.
Mathematically, the operators that describe them, often written as gamma, they have two key properties.
Okay.
First, if you apply the operator twice, you get back to the original state gamma dagger gamma.
Right.
Which is related to being their own antiparticle.
Gotcha.
And secondly, they interact with each other in a very specific way, known as anticommutation.
Yeah. Gamma, dame,
That anticommutation sounds familiar.
Yeah.
That's another signature of fermions, right?
That's right.
Yeah.
And what makes these Majorana zero modes even more intriguing is that they exhibit what are called non-abelian statistics.
Okay.
And this is a type of quantum behavior that's more complex than the familiar way particles like bosons and fermions behave when you swap them.
Right.
It's like if you have two objects and you swap them, the result depends on the path you took to do the swap.
Oh, wow.
Yeah.
Okay, non-abelian?
Yeah.
That sounds like it could have some very unusual consequences.
It does indeed.
Yeah.
A key example of where these Majorana zero modes can pop up is at the ends of a theoretical one-dimensional chain of a special type of superconductor called a p-wave superconductor. And this is described by a theoretical model called the Kitaev chain. And it has a Hamiltonian that looks like this. H mu sum, Shedabor, Schneider CIFC plus delta sumi. Schneider CI plus 1 dagger plus HC.
Oh, wow.
Yeah, it's a bit of a mouthful.
Yeah.
But basically, under certain conditions, specifically when the energy cost of having an electron, represented by mu, is smaller than twice the energy it takes for an electron to hop to a neighboring site, 2t. The system enters a topological phase. And you get these unpaired Majorana zero modes appearing at the two ends of the chain.
So these Majorana zero modes are like isolated special entities just hanging out at the edges of this superconducting chain.
Yeah, exactly. Oh. And this physical separation gives rise to some really unique and potentially very useful properties. So they can essentially store quantum information in a way that's spread out, making it much less vulnerable to local disruptions. And this inherent protection arises from the topology of the system. And it suggests a built-in resilience to errors.
And that non-abelian statistics we talked about, that allows for a process called braiding.
Yes.
Which could be a way to actually perform calculations on quantum information.
That's right.
Okay, so braiding.
Yeah.
Like physically moving these Majorana zero modes around each other.
Yeah, precisely. If you carefully swap the positions of these Majorana zero modes in a really controlled manner, it corresponds to performing a quantum operation, which is a fundamental building block of quantum computation. And this topological effect could potentially enable quantum logic operations that are inherently protected from errors without even needing complex error correction methods. It's kind of like tying a knot in a rope. You can wiggle the rope around all you want, but the knot itself remains
unless you untie it.
Exactly. Majorana qubits are aiming for that same kind of stability for quantum information.
This sounds incredibly promising for the future of quantum computing.
It really does.
So have we actually seen evidence of these Majorana fermions in real experiments?
Well, the search for Majorana fermions in these solid-state systems has been a really active and exciting area of research, and there have been some significant breakthroughs. A primary experimental approach is to use these incredibly tiny semiconductor wires made of materials like indium antimonide in MIDI or indium arsenide in A's, and then they carefully connect them to conventional superconductors.
What's the idea behind this kind of setup?
Well, these semiconductor nanowires, when they have strong spin-orbit coupling, which is a kind of interaction between the electron's spin and its motion, and they're placed in a magnetic field, can be engineered to develop a special kind of gap in their electronic energy spectrum. It's called a topological gap.
Okay.
And when these nanowires are brought into contact with a conventional superconductor, the superconducting properties can essentially leak into the nanowire,
right?
Potentially creating the conditions for Majorana's zero modes to form at the very ends of the wire.
And how do scientists actually try to detect these elusive Majorana states in these setups?
Well, one of the key experimental signatures that they look for is something called a null bias peak. In measurements of differential conductance.
Right.
It's essentially a sharp spike in the electrical conductance measured at 0 voltage.
Right.
And the theory predicts that if Majorana's zero modes are present at the ends of the nanowire, they should give rise to this characteristic peak.
And have we seen this null bias peak in experiments?
Yeah, we have. The first compelling evidence came in 2012.
Wow.
From a team led by Leo Kuenhoven at TU Delft.
Right.
They observed a really clear null bias peak in their experiments. And this really generated a huge amount of excitement in the field as like a potential first glimpse of Majorana Fermions.
Wow.
Since then, other research groups, including those at Microsoft's research labs, have also reported similar observations using slightly different setups involving planar superconductor hybrid systems. So essentially flat two-dimensional structures.
Right.
And IBM has also been exploring alternative platforms, such as looking for Majorana states, trapped in tiny magnetic vortices within superconductors, and in superconducting quantum dots.
That sounds like a lot of progress on multiple fronts.
Yeah, it really is.
But you did use the word potential, first glimpse.
Yeah.
Are there still some, like, lingering doubts?
Yeah, there are. Or, like, alternative explanations for these observations. Absolutely. While the observation of null bias peaks is very encouraging, the interpretation of these results isn't always straightforward.
Right.
The challenge is that other phenomena, like the formation of other types of special electron states, called Andreev bound states, or even just tiny fluctuations in electric charge within the system, can sometimes produce very similar experimental signatures.
Wow. So it can be hard to tell.
Yeah, it can.
Yeah.
So definitively saying we've unequivocally detected a Majorana fermion based solely on a null bias peak is still a challenge. It's not quite the smoking gun we'd ideally like to have.
So it's like a promising hint, but not a slam dunk just yet.
That's a good way of putting it. There are also significant technical hurdles involved in these extremely delicate experiments. Maintaining the absolute purity of the semiconductor nanowires is really critical. As even tiny imperfections can disrupt that fragile topological state. And precisely controlling the applied magnetic fields and maintaining those incredibly low temperatures required for superconductivity are also very demanding experimental feats. And there are still open questions about the exact nature of the signals that have been observed and how reliably we can manipulate any potential Majorana states that might be present.
So while the experimental evidence is definitely intriguing and promising, it's clear that this is still a very active area of research with ongoing challenges in getting that definitive confirmation. Let's switch gears back to why all this effort is so important, like the potential impact on quantum information. How could Majorana Fermions revolutionize the field of quantum computing?
Well, the real game-changing potential lies in this concept of topological qubits, which are quantum bits, based on these Majorana zero modes. Just as a quick reminder, a regular bit in a computer is either a 0 or a 1. But a qubit, the fundamental unit of quantum information, can exist in a superposition of both states at the same time. Alpha 0 wrangle plus beta 1 wrangle.
So much more flexible. And powerful than a regular bit.
Exactly. Now, a topological qubit can be formed by using a pair of spatially separated Majorana zero modes. Let's call them gamma 1 and gamma 2. These two Majorana modes can be thought of as combining to create a kind of effective Dirac fermion state. Cfrac 1-2, gamma 1 plus I gamma 2. The two states of the qubit, 0 wrangle and 1 wrangle, then correspond to whether this effective Dirac state is empty or occupied.
So the quantum information is encoded in whether this combined state of two Majorana modes is on or off.
That's right.
Yeah, okay.
But the real advantage here, the reason why this is so exciting for quantum computing, is the inherent protection that these topological qubits offer. Because the Majorana zero modes that make up the qubit are physically separated from each other within the material, the quantum information stored in them is intrinsically protected from local disturbances and noise.
Gotcha.
So this gives them the potential for much longer coherence times, which is the amount of time they can reliably hold quantum information.
Okay.
And a built-in fault tolerance.
That sounds like a massive leap forward compared to current qubits.
It could be.
Yeah.
Yeah.
That are so fragile and prone to errors.
They are, yeah. And remember those non-abelian statistics we talked about earlier?
Yeah.
That's what enables the braiding operations.
Right, okay.
Because Majorana Fermions have this special anti-commuting property.
Yeah.
Gamma, 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 gamma.
Right.
So if you carefully swap two of them around each other, it doesn't just introduce a simple phase shift like it would with regular particles.
Okay.
It performs a more complex, non-trivial operation on the quantum state.
So physically moving these quasi-particles around in a controlled way is like performing a quantum gate operation.
Precisely.
Okay.
And by carefully orchestrating these braiding movements of the Majorana zero modes, we could potentially implement all the necessary quantum logic gates to build a functioning quantum computer.
Wow.
And the really attractive aspect of this approach is that these braiding operations are topologically protected. This means they're inherently much less sensitive to errors caused by local noise and imperfections.
Okay.
So this paves the way for fault-tolerant quantum computation.
Wow.
Without needing the complex and resource-intensive error correction schemes that are required for other types of qubits.
So no more needing to dedicate vast amounts of resources.
Hopefully not, no.
Yeah, to correct errors just caused by the environment.
That's the idea.
Okay.
The topological protection offers a very promising route towards achieving much more robust and scalable quantum computation.
Okay, so this all paints an incredibly exciting picture.
Yeah?
For the future of quantum technology.
Yeah, it does.
So what's the current state of play?
Yeah?
Are we like on the cusp of seeing topological quantum computers become a reality?
Well, the field is definitely buzzing with a huge amount of activity. As we've discussed, major players like Microsoft, the research groups at TU Delft-Quidtech, Google, and IBM are all actively exploring different pathways to build fault-tolerant quantum computers. And Majorana Fermions are a central focus for several of these efforts. However, it's important to be realistic. There are still significant technological hurdles that need to be overcome before we see like practical large-scale topological quantum computers. These include further refining the quality of the materials we use, achieving more consistently reproducible experimental results, demonstrating reliable and fault-tolerant braiding operations, and ultimately scaling up the number of qubits that can be controlled.
So still some significant engineering challenges ahead.
Definitely.
Okay.
Yeah. Current strategies for building these systems involve continuing to improve nanowire-based approaches, exploring new types of planar quantum materials that might naturally host Majorana states, and further investigating the potential of vortex-trapped Majorana states in topological superconductors. And the long-term impact if we are successful, could be revolutionary for quantum informatics. We could see the development of fault-tolerant quantum computers capable of tackling problems that are currently completely beyond the reach of even the most powerful supercomputers. And breakthroughs in areas like advanced encryption methods. It could also have huge implications for material science. Potentially leading to the discovery of entirely new materials.
Wow. With exotic and useful properties. And more energy-efficient electronics. And even on a fundamental level. It could provide new insights into unanswered questions in physics. Such as the true nature of neutrinos. And the mystery of dark matter.
It's mind-boggling to think that these incredibly fundamental and elusive particles could have such far-reaching and transformative consequences.
It really is.
So to bring it all together, Majorana Fermions. Truly enigmatic particles that hold the potential to fundamentally reshape the landscape of quantum technology as we currently understand it.
Absolutely.
Yeah.
It's been a fascinating journey.
It has.
Starting with Ettore Majorana's groundbreaking theoretical work, exploring their potential to emerge in this exotic realm of topological superconductors. Looking at the ongoing and incredibly challenging experimental quest to definitively prove their existence. And finally, considering their remarkable promise
for ushering in a new era of robust and fault-tolerant quantum computers.
It really does make you think about the future, doesn't it?
Yeah, it does.
Like, what other fundamental secrets are lurking within the fabric of reality?
Who knows?
Yeah. It's waiting to be discovered.